video, we will start with an introduction to Synopsys and its automatic design search tools. We will talk about the binary search method briefly and use a 7-element system design search as an example to illustrate the automatic design search tool in Synopsys. We will also discuss the tolerance characteristics of the same system when searched with the tolerance desensitization goals in Synopsys. Then we will introduce the concept of a saddle point method and how to use the automatic element insertion and deletion tools built on this method to improve the 7-element system. We will start with an introduction to the Synopsys Lens Design software and its automatic design search tools. Synopsys was first launched about 50 years ago by Don Dilworth, an expert optical designer. He created the word synopsis to stand for synthesis of optical systems. It comes with a complete toolkit for demanding optical designs such as zoom lenses, microlithography systems, and aspheric systems. It also comes with some very unique features, a fast optimization algorithm, and a set of innovative and powerful automatic design tools. Optimization is the heart of modern optical design software. It is a piece of numerical algorithms that can improve your starting design by changing the lens parameters to minimize the design merit function. Synopsys runs on the powerful PSD pseudo-second derivative algorithm created by Don Dilworth. By considering the effects of the higher order derivatives, the PSD method converges faster into a deeper minima. Let's take a look at this example. We start with a system consisting of 7 pieces of glass plates, all with a thickness of 1 millimeter and a refractive index of 1.5. This is not much of an imaging system to speak of. We set up an optimization macro here of no more than 20 lines of script. Let's run it. In less than 1 second, it turns this all-flat system into a decent imaging system with an average RMS of 6 microns over the 3 fields. Mathematically, optimization is a difficult problem in a hyperdimensional space, especially when you have a complex system and many designs or optimization variables to consider. As an analogy, we can visualize the optimization space as a mountain range with many minima. The 7 glass plate system we just examined corresponds to the worst imaging system you can have that is standing on the top of your optimization mountain. You want to drive it down the slope to reach a lower merit function. The path you take will determine where you will land. For example, if you start in this direction, you may end up here. In this direction, you would end up here. Usually you take a path that is well traveled based on other designers' experiences, patents, or previous designs because you don't want to go into a wild chase or go down a path that leads to nowhere, which is safe, but at the same time it limits your design form. Now imagine that you can ask for a virtual team to help you explore the mountain range by sending out virtual explorers down the mountaintop at different directions. That is, a different starting configuration or trial system or design form, and report back to you about which one will bring you to a lower merit function minima. That is the concept behind the automatic design search in Synopsys. The distance and the speed you can jump downhill depends on the performance of the optimization engine. The powerful PSD optimization algorithm in Synopsys can help you get to a deeper minima faster and makes the automatic design search powerful. There are 2 automatic design search algorithms in Synopsys: the binary design search and the saddle point method. They can help you find realistic starting points quickly and help you explore the design space and discover many new design forms. Sometimes these design forms may have better performance not realized by conventional design protocols. Let's see how the binary search method works. When you start the binary search method, Synopsys generates a family of lenses based on the number of elements that you requested for the system. For example, if you request a system of 7 elements, then Synopsys will generate 128 trial systems and use 7 bits to represent the trial systems. Then it will assign initial power, positive or negative, 1 or 0, to each element to create the trial system. Each sequence represents 1 trial system. Using the mountain range analogy we discussed before, this is like assigning the downhill direction for the trial system. Then for each trial system, Synopsys will optimize it according to the specific goals entered by the user. Then it conducts simulated annealing to refine the system. That is the same as driving the system down an optimization mountain on a certain path to reach the minimum. This is the powerful design search technique in Synopsys. Now let's first look at a basic DSEARCH example for a 7-element system. Then I will introduce a new DSEARCH feature that aims at searching systems that are less tolerance sensitive based on the tolerance desensitization concept introduced by Don Dilworth. To do the DSEARCH for a 7-element system, we first set up a DSEARCH macro. You can enter the commands in the macro editor directly if you are familiar with the scripts and synopsis. Or you can use the DSEARCH dialog in the Optimization and Design Search menu to assist you. Here is the DSEARCH macro. The first block here is the system declaration. Here are the goals with the special optimizations we added to the search, and here you also see the optimization and annealing iterations. Now let's click at the Run button to start the DSEARCH process. When DSEARCH is done, Synopsys automatically creates an optimization macro based on the goals and other optimization requests entered in the DSEARCH macro. You can then run this macro to further refine the starting design. The DSEARCH process retains the first 10 best candidates. This graph is a summary of them. The top one is the best candidate. You can experiment with the other candidates to explore different design forms, and sometimes the other candidates can also be optimized to be a good design. This is the best candidate returned by the DSEARCH. Now let's look at the RMS curve of this system to evaluate its performance. Click at the Image Analysis menu, select RMS, select Overfield, then run it. Here is the overfield RMS curve for the primary color. It's already in the micrometer range. Now let's modify the DSEARCH macro by adding the DSense goal. DSense stands for Tolerance Desensitization. It utilizes a special set of optimization targets that involve the control of the third-order aberrations to relax the tolerance sensitivity of the system. This is the top candidate it returns. It has a somewhat different design form than the previous one. Let's compare the RMS of these two systems. We see that in general, the system with the tolerance control has a better performance with a smaller RMS over the fields. Now let's look at the budget tolerance analysis of these two systems. To do a tolerance analysis, we click at the Prototype Readiness menu, select BTOL to open the budget tolerance dialog. For this analysis, we will accept most of the default settings. Using a confidence level of 2 sigma, accept all the default ranges for the tolerance variables, use all test plates, make no adjustments, and for the quality descriptor, we will use the tolerance criteria of 0.1 wave. Then click Go. Synopsys starts doing the analysis. Once it's done, the analysis results are printed out in the command window here. It includes a section of the inverse sensitivity analysis for each surface, a section of the budget tolerance analysis for each surface, an element fabrication tolerance, as well as an element assembly tolerance. Here is the comparison of the radius tolerance measured in fringes at each surface of the two systems. The blue curve is the result of the basic system, and the orange one is the system designed with tolerance desensitization. This is the thickness tolerance at each surface in millimeters and in log scale. This is the wedge tolerance of each element measured in arc minutes. Element 3 is more relaxed with the tolerance desensitization result. Irregularity tolerance at each surface in fringes. The system designed with tolerance desensitization has better performance. Tilt tolerance at each element. Element 3 is more relaxed with the desensitized system. Finally, this is the decenter tolerance for each element, measured in millimeters and displayed in log scale. We can see that most of the tolerance requirements are more relaxed with systems returned by the DSEARCH with tolerance desensitization goals. By taking into account the tolerance considerations early on in the design process, instead of addressing tolerance afterwards, the automatic design tool in Synopsys can help find designs suitable for manufacturing right from the beginning, and therefore increase productivity of your team. Next, we will talk about the saddle point method and how to use the automatic element insertion and deletion tool. The saddle point method employs an innovative algorithm to improve your system by adding design degrees of freedom intelligently. We have all heard about the concept of using degrees of freedom in optical designs in school. However, how do you use it? Which degrees of freedom are you to use in which designs? These are the questions with no direct answers. You basically need to figure it out by trying, and that's why numerical algorithms will be your best tool. A saddle is a shape that curves up in one direction and down in another direction. A lot of times during the optical design process, due to the selection of the optimization variables and the available degrees of freedom in your design, the optimization process may be going along this line and settle at this point, a local minimum, and you think that is the design. However, what if you can go down this green line and get to this lower minimum and thus get a better design? But how can you go from this red line to this green line? One method is to add degrees of freedom for your design. By adding this thin shell to this element, it increases the degree of freedom to the design and thus allows the optimization to go in a different direction that may lead to a lower minimum. This is the concept behind the saddle point algorithm in Synopsys. Now let's see how it works. Here is a simple script to build a 5-element system using the saddle point method. Let's run it. You see that Synopsys is adding lenses to the system, one lens at a time. 1, 2, 3, 4, 5. And at the same time, it is changing the lens parameters to optimize the system until it is built completely. If you are doing it manually, it would be very tedious to go through all these configurations or trial and error, especially if you are designing a complex system. However, with the help of Synopsys, it becomes quite easy. You can use the saddle point method to build up a system from zero. That is the saddle point build in Synopsys. Or you can use it to scan through a system to find where to add an element to improve the system performance. That is the automatic element insertion tool. When you run AEI, Synopsys will insert a thin shell to each element, optimize the system to see if adding the element at the trial location can help drive the merit function down. You can also use it to scan a system to find out where to delete an element with the least impact to the system performance. That is the automatic element deletion tool. AED is the reverse of AEI. It scans through the system and reduces the thickness of each element to find out which element to remove. It also finds where to introduce an aspheric surface that would do the most good. That is the automatic aspheric assignment tool. Now let us again use the basic 7-element system from the last section to show how to use these tools. This is the optimization macro created by the DSEARCH process for the system earlier. To use the AEI method, you only need to add the AEI command at the top of the macro. Then run the macro. Here is the system after AEI. It has one more element than the starting system. When we compare it using the system we got using the tolerance desensitization DSEARCH method, we notice that they have a similar design form, especially for the first group. When we plot it in RMS against the original system, we can see the improvement clearly. As an exercise, we will run another AEI to the system and turn it into a 9-element system. Here are the RMS curves of the 3 systems, 7-element, 8-element, and a 9-element. You may say this is nice, but I know that my manager doesn't want to spend the money to add 2 more lenses into the product. So let's see if we can use the automatic element deletion tool to remove the lenses. Again, using the same optimization macro created by the DSEARCH process for the system earlier. This time we will comment out of the AEI command and add the AED command at the top of the macro and click on this button to run it. This is the 8-element system after running AED. Let's apply another AED to reduce it back to 7 elements. Now let's look at all 3 7-element systems we have designed using the different methods. First, the original system by basic DSEARCH. Second, DSEARCH with tolerance desensitization. Lastly, 7-element systems designed with AEI and AED tools. And let's look at their RMS curves. We see that the second and the third systems both have improved RMS curves. In this video, we've introduced you to the DSEARCH method, the saddle point method, and the automatic element insertion and deletion tools in Synopsys. You can use these tools to find realistic starting points,
explore the design space, and improve your system performance.
Please visit our website to learn more about the Synopsys automatic design search tools and other features, such as an ultra-wide field design using DSEARCH, DSEARCH, which is the automatic design search tool for zoom lenses. Check out a design tool for free-form, off-axis mirror systems easily laid out and optimized in 3D space for you. Synopsys is a fast, powerful, cost-effective program with a perpetual license. Contact us for more details or to request a free trial.